Hello everyone, welcome. We're just going to give it a minute to let people join and then we'll get started. Great, so the numbers are just coming up. We'll give it another 30 seconds and then we'll get started.
Becky, do you hear me?
Yes, I can hear you fine. All good. Perfect. Great. So hello everyone and welcome to the webinar introducing predictive maintenance as a service. My name is Becky Christmas. I'm a project director at Reuters Events and I focus on the downstream events and content. Just some information before we start. This webinar will last approximately 1 hour and is being recorded. So we will send you the full audio next week in case you wanted to listen again. There will be 15 minutes audience Q&A at the end, so please use the Q&A box at the bottom of your screen throughout the webinar, and we will answer them in the designated time at the end. This webinar today will be led by Precognize, a predictive maintenance company addressing the process industry. It is part of SAMSON Group, headquartered in Frankfurt, Germany, specializing in control valve engineering. Precognize solutions Samguard combines sophisticated technologies of AI and HI, SME's knowledge, to achieve maximum asset availability and performance. Its patented and unique technology with Samsung's 100-year plus of expertise and global presence are set to expedite the digital transformation journey of the process industry. The speakers for the webinar today are Shen Levinsky, CEO of Precognize, and Maya Rubin, Analytical Monitoring Engineer of Precognize. So let's get started. I'll hand over to Shen. Thank you.
Okay, thank you very much, Becky. Thanks for the introduction. And thank you all for joining, especially the ones from Europe and Asia at this late hour. As Becky mentioned, we'll talk about the predictive maintenance as a service today. Before we do that, just a quick addition to the introduction. So Precognize is based in Israel, high-tech company, was announced by 2018 by World Economic Forum as one of the technology pioneers. Today we're part of SAMSON, so actually we're now combining our innovation, technology, machine learning and so on with years of experience in the process industry, which SAMSON brings, and of course the worldwide presence, more than 4,500 employees, 76 subsidiaries worldwide. Now our solution, as was mentioned, is specifically designed for the process industry, and there are some parameters which are very different between this industry and any other industry and any other type of predictive maintenance. And as you can see at the bottom, we're serving customers from Europe, Asia, US, some of the big ones, some of the medium-sized ones, and even small ones. And we're also partners with the leading companies in this area, such as Siemens, Oisasoft, and more. So this is a little bit about us. And now let's get to the business. When we're talking about predictive maintenance, we're talking about the very clear and precise use case. Okay, it's very clear that if we identify a failure of a part, a failure of equipment at its early, at its commencement, we are going to save money. So if we actually identify when it's only started to make some small signs that something is wrong, and as consequences of that, we just added oil to the pump and solved the problem, versus a situation where later on the pump continued to to rotate and to create damage, and we had to replace the bearing. So it's the cost of repair, of course, the cost of downtime, and so on. So the use case here is clear and flat, and you don't need many explanations about that. Now, when we look at our maintenance costs, though, we see that most of the money that we spend within our budget, maintenance budget, is about turnarounds. Okay, this is the big money. The second part, which is a little bit smaller, is all these failures, all these maintenance events that are happening on a daily basis. Here we have a problem with a control valve, there with a pump, and so on and so forth. And these things are happening on a daily basis. Now, if we look at the split by the type of equipment, try to imagine when was the last time where a big, expensive compressor has failed on you. Okay, usually it doesn't happen. Okay, so actually, if we divide the cost by type of equipment, what we can easily see is that the turnarounds, we invest a lot of money around the expensive rotating equipment, and we also invest, of course, in the regular equipment, pump valves, the condensers, heat exchangers, and so on. But in the failure side, it's mostly, and luckily for all of us, mostly it's about regular equipment, not those most expensive equipment. Now, if we look at the opportunity here in predictive maintenance, we see very little opportunity around these expensive rotating equipment. Okay, because most companies will not take the risk of postponing maintenance for expensive equipment. And it's not very efficient because these things need to be coordinated in advance and so on and so forth. So if you're asking me now, should I create a very good predictive model for my most expensive compressor? Maybe you should if you didn't do it before, but would there be a real value or real benefit or really immediate benefit? I don't think so. The same applies a little bit less to the regular equipment, because there we start seeing companies prioritizing within their turnarounds, delaying some of the maintenance for some of the parts which have bypass or that do not require to really take down the plant in order to replace it. So there we see an opportunity in the longer term to really prioritize parts and replace them on the go. The most immediate opportunity that we have with predictive maintenance is to prevent those failures, okay? Because this is an immediate thing. This is something that can be done, and this is where we see value that can be gained. So now when we're looking at predictive, at these failures, the main problem with failures is that they can happen everywhere. Okay, I don't know in advance which parts are going to fail, whether it will be heat exchanger or furnace on the static side, or a fan or a blower or a pump. Okay, everything can fail. Now, the big compressors and turbines you probably already covered with all kinds of things in your rules and so on in your control. The problem is that all the rest are creating actually almost 100% of your failures in the regular operation. And this is where your problem is. Now, this is exactly what we're looking at. So Samguard is actually our product for predictive maintenance is actually covering exactly that. We're covering the entire plant, whether it's a small valve or whether it's a big compressor and everything in between. Okay, we basically take all the data, the process data, and we analyze all these parts together. Now, the nice thing about these parts, which each of them can fail, is that you're already collecting a lot of process data about them. Okay, you collect flow and pressure and temperature, and in some cases you even collect more equipment-related data like vibrations. Okay, all this data is collected now, is sitting in your historian. Now, if you, and actually, in most cases, before the real problem, before a problem really occurs, there are some small signs in the data that something is deviating, something is going wrong. Okay, so data is there, and in most cases, the potential problem will be reflected in the data. And if we as people, and you as people in the plant, the process engineer, and any other person in the plant could actually look at all this data, all these thousands of sensors, monitor all the trends, apply your knowledge, what you know about the plant, together with looking at all these data, probably you could have prevented many of the failures. The only thing is that usually the data is not as clear as you see here. It's much more complicated. And the other thing is that no person alive can actually look at thousands of sensors all the time. You look at 10, you look at 20, you look at 50 tags, but you cannot look at everything, okay? And this is exactly where AI comes to place, okay? Because the software can look at thousands of sensors all the time and try to find when these small deviations are happening, okay? And this is exactly what we did with Samguard. We actually monitor all this data together, but we're not doing just that. What we're doing in addition is we're trying to imitate some of the knowledge that you would apply if you were looking at these trends with your eyes. And we're trying to grasp as much knowledge as possible. And most of this knowledge will be found in the PNIDs, and some of it will be gathered from your team, from the engineers on site, through our Samguard studio. And this is what we created here is a very fast process. Okay, we don't know, or the software don't know everything you know in the plant, but it knows enough, just the bare minimum, in order to create a causality graph. Okay, in order to allow the software, wherever there are those small deviations, to think like you would think and determine, is it a real problem, or is it just some noise that you should ignore? So this thing, which we built in a very fast 2 weeks process, actually works in conjunction with the machine learning. So the machine learning is looking for the anomalies, and the causality graph is actually telling us, is it something that the process engineer or any other engineer on site would think, yeah, it makes sense, it's a real problem, we should take a look, or not, it's just noise, and then we avoid it. And this allows us to actually come up with only an average of 5 alerts a day. Okay, 5 alerts, some of them relate to mechanical problems, some of them relate to instrumentation problems, some of them relate to electrical problem. And remember, we're using mostly process related data, so some of them relate to deviations in the process. Okay, so, and I think each of the listeners in the webinar now will agree that 5 alerts a day is not a big deal. And in very stable plants, it will be much less. So no problem. If you look at the benefit side, and this is a slide that was prepared by one of our customers, you can see that when they started Samguard implementation, actually their availability and their reliability factor has improved dramatically, okay? The cost of labor, which related directly to maintenance, has been reduced because they know in advance what kind of things they would need to do, and they're not surprised by unexpected failures. So the promise here is huge, okay? And here I'm switching gears to a different atmosphere, because the value is clear and the technology is there. But the one question I would like to ask you now is actually, if we're looking at this split that I showed earlier, and we're talking now about failures, my question to you is, who is in your organization is really interested in preventing these failures in advance? Who is the person that's on his task list, KPIs, bonus plan, whatever, appears prevent failures ahead of time? And what you would find, I think, in most plants, maybe not all of them, but in most of them, is that the typical plant accountability doesn't really cater for failures. Because if you look at the plant or unit or production manager, it depends on terminology of each plant, you see this person is actually responsible mostly for more production. Okay, as much production as possible. And, of course, they would want to prevent failures. Of course, they would want to cut on the budget of the maintenance, but it's not on their task list. If you look at the process engineer, of course, process engineer would want to have a smooth operation, but they look at process efficiency, they're reacting to problems. Is it their main task now? Probably not. It may be in the future, but it's not their main task. If you're asking them today, is your task to prevent failures in advance? Probably not the main one. And then you look at the maintenance manager, which supposedly should be the right person. Okay, they hold the maintenance budget, and probably in their KPIs there is the mean time between failures and any other parameters which reflect the need for prevention of failures. But the issue we found over the years of experience of working in process plants is that the maintenance team, according to the current behavior, the current culture, is mostly reactive. Either they do planned maintenance or they react to work orders from production. And again, I'm not here to, I'm sure there are exceptions, and I'm sure there are plants that are working in a different way, but in general, the regular maintenance behavior is that this team is coming in to solve existing problems, and it's reacting to planned maintenance. And the other thing which we need to remember is that the maintenance team, although related to the equipment, has usually more loose connection to the process changes. Now, remember that our alerts, our data, the data that we can use for predictive maintenance is actually process data. Okay, so this again creates some kind of discrepancy between what the maintenance manager is used to and what the maintenance manager has on his task list versus what you need in order to prevent failures. And this basically summarizes the main issue. There is great potential for PDM, and you see that companies that implement this successfully, so great value, but there is no immediate stakeholder in many of those plans. And therefore, what I would say is that predictive maintenance should be viewed not as a technology change and not as a technological change, but as a cultural change. Okay, and it's basically saying that, yeah, you can worry about technology, you can worry about false alarms and how many false negative, how many false positive you have. This is all very important, yet this is not the main issue. The main issue is how do we find the right stakeholder within the plan. Now, I was planning to run a poll right now and ask you some questions. The only thing is that I don't see it on my screen now. Becky, can you pull up the poll for me? Okay, great. So if you would be kind enough and answer, it's a very simple question about cultural change. And the question is, did you ever apply to your plant a project that requires a cultural change? Okay. Yes, maybe Six Sigma, maybe Agile, maybe something else. Just answer yes if you did something else from the same category. Okay. And I'll give you a second to answer that. And if we can move to the second question, please. Becky, great. Okay, so for the ones that did that did some kind of project like this, which required cultural change. We're kind of interested whether, first of all, was it a success or not? And the other thing is whether you actually used any external consultant. And I'll give you a second here to answer. Okay, great. And just okay. So it's interesting to look at the results as we're looking. Yes, the project was success. We have 31%. Yes, and the project failed. We have 4%. And the really interesting thing is no, and the project was a success, and no, and the project failed. Okay, so yes, we can say that you can succeed. You can succeed anyway. By the way, the statistics about the Agile and Six Sigma projects show that about 60% of the projects are failing because they require a cultural change. So basically, what we're saying here is that the main issue that we see is that there is a gap. Okay, there is a gap between the value that predictive maintenance can do, the technology, which is beautiful, and the stakeholder within the organization. And here you have two options to go about it, at least from our experience. Okay, the first option is internal. Okay, select a champion within the organization, and after selecting this champion, manage and support him from high level, at least at the plant level. And the important thing here to remember is if you're selecting these internal resources, do not select a resource that is already occupied 100%. And if you're selecting a person that is already occupied 100%, remember to remove some of the tasks from his task list so he will have enough time to run this predictive maintenance project. And one thing I urge you to do is not to ask this internal person, not to give him the task of test the technology and let us know if it's good. If you're not sure of the technology, ask for references. Go and visit customers who have already implemented the technology. Ask them every possible question about the technology. Don't give this poor process engineer who is now trying to make the best for his plant the task to test technology. And believe me, the technology is not your problem. The real thing that you should ask this guy to do, or this lady to do, is to lead the cultural change. Okay, lead the cultural change that will enable us to benefit from predictive maintenance. Lead the process where the maintenance manager react, where the control room react, where everybody is reacting in the right way to the fact that we know in advance that something is going to fail. And this is the key aspect here. Not the technology, not the false positives, not the false negatives. This is something you should check in advance by asking references. The thing that you need to have there is a person that lead the cultural change and have enough time and enough management support. The other option which we're offering here, and I think it works very nice in several cases, is to do what we call analytical monitoring center. And this is saying, listen, the internal team needs to have some kind of mitigation, some kind of digestion between what the technology can provide and what the team can consume given their current responsibility in the plant. And the idea behind the Analytical Monitoring Center is that you're placing a person there who is dedicated for the solution, who is actually his own only task is to make life easier for all the other stakeholders. Okay, and help setting the responsibility so later on eventually, maybe it will go into the planned regular operation. So, and this person can be on site, okay, working 100% within a big refinery or a big site. It can be somebody who's working remotely, and we have projects where we are monitoring from here. We're monitoring plants all over the world in communication with the engineers all over the world. And it can be something hybrid, where the engineer is in the plant for some of the days, creating the right relationship, and then do some of the work remotely. And what it means in practicality is that we have this powerful machine learning and AI algorithm, which is great. When data is flowing in, the machine learning will assess it and will decide, okay, do we have a problem here or not? And if there is a problem, it will pop up on the analytical monitoring engineer screen. And this person, as Maya will demonstrate in a second, is actually responsible to do the first screening, the first root cause analysis for the team in the plant. And once it is done, he can communicate it to the plant team, discuss it with them, get the feedback, understand what's going on, and eventually, and not less important for projects for predictive maintenance, eventually close the event, understand what the value was, and make sure that we articulate not just the fact that we actually fixed something ahead of time, but what value have we gained from it. So later on, when management will ask, how good is the predictive maintenance project going? You have a clear understanding of what the benefits. So this is basically the daily process that is happening within the Analytical Monitoring Center, the AMC. And with that, I would like to take this general overview and go deep into the details and ask Maya Ubin, who's a process engineer in our team, to actually describe her day as an analytical monitor engineer in several projects, both hybrid and remote. So Maya, the floor is yours.
Thank you, Chen. Okay. Hello, everyone. So my name is Maya. As Chen said, I work as a process specialist in Precognize. I work actually with you on site. Some of the services with the clients are hybrid, which means that part of the week I work on site and the other days I work remotely. And some of the clients are using our remote service. And today I would like to elaborate more about the Analytical Monitoring Center. So what are the added values? Robert? Okay, I'm sorry. I didn't do the share. Do you see my screen now?
Yes, we can see your screen. Just need to make it. Yeah, there we go.
Okay, sorry, apologies. So again, so what actually the added values of the Analytical Monitoring Center? I did. Do you see my screen? Is it okay?
Yes, we can see your screen now.
Okay, so the added values of the Analytical Monitoring Center. So first of all, as I said, some of the week I'm actually on site, and therefore you get all the time an online monitoring of the reported events very close to their appearance, which means actually that you get a very quick and efficient response. Additional added value is the management and the follow-up after the open action items. Well, I'm sure you all can understand what I'm talking about, that the everyday life on site is very, very dynamic, and you get all kinds of surprises, and all the planned schedule is many times postponed, or some action items are missed. So I am there in order to tell you and to manage and follow up all the action items that comes up from the events from Samguard, and I following up until the execution. And lastly, but actually I find it as the most essential one, is establishing a meaningful cooperation with you, with the team in the plant. I'm a process engineer, that's true, but you are the one with the deepest knowledge about your process. So I bring you the data, I bring you the Samguard's smart algorithm, and I bring you my process orientation. But the key to the best added value is actually our cooperation. So let's see how does a typical day in the analytical monitoring center looks like. So first in the morning, I catch up with the process engineers. I'm asking them if there were some significant things, or maybe there are some planned action items for today that I should be aware of. Then I take a look into the shift log, where the controlling room, the shift manager left his comments. This is very important for me in order to know what happened during the night. Next thing is the planned morning meeting. This is something very unique to the Analytical Monitoring Center. And for me, it is very efficient, because in the plant morning meeting, you see and hear all the plant stuff. You hear the maintenance, you hear the environmental department, you hear the process engineers, and that really gives me the full picture of the day. Next step in the day is to actually to review the events that came up in the process. I'm filtering the most important and interesting findings that I see there, and updating the relevant engineer. Together we find the root cause. Now it might be a very simple and easy to understand root cause, but it also might need a deeper investigation. But the goal here is to find the root cause. After we found the root cause, there are action items. So it might be if we found a mechanical or instrumentational, for example, failure. So that would be a SAP or a job for the maintenance to do some action. And it might be also a process problem. And then the process engineer will have his action items. For example, if an operator did some unexpected change or undesired change. And this is where the controlling and the follow-up is coming into an action, because it is very important for me that no failure and no action item will be missed. So I'm making sure that to follow up until the resolution. And lastly, of course, I'm updating the champion of the plant. Now, please let me share with you some events that I found to be very interesting to emphasize the additional value of the Analytical Monitoring Center. So the first case we're talking about is the flare ceiling water level controller blockage. You can see on the screen, the green line and the purple are representing the level in the flare, the drain level. And actually, there is a significance for a specific volume in the flare, in the ceiling water in the flare, in order to allow the gases to go through out. And when the controller is wrong, when you are not able to maintain your level, so you get a high pressure, and you get a problem with the gas flow. Actually, this event was happened during the weekend at the evening, but I found it to be important enough to contact the process engineer. So I called him, but unfortunately, the first conclusion was wrong. It was referred to some other process change that happened during that time. And at this point, I have to say that we're dealing with a very complicated process. We're not talking about a simple one. We're talking about a huge, huge plant with more than 600 valves, with thousands of tags. So it's just human to maybe refer it to a different reason. But the AMC ongoing attention enabled lastly to find the real cause, which was the drain level blockage. Now, I have to emphasize at this point that the first and the repeating events were really provided very early. And this is very, very important for problems that are developing in several hours. Next case is talking about a flare evaporator steam trap leakage. The trends that you are looking at are the temperature controller of the evaporator. You can see that the mode, the OP, and the set point of the valve are stable, but on point A, something is happening with the PV. The temperature is increasing, and we don't understand what happened here. So the first alert of Samguard was created here, and the plant team took it and thought what could be wrong. And the first guess was the temperature controller is not working well, and therefore it is very difficult to maintain the temperature in the evaporator. So at point B, you can see the maintenance, and then in point C, they brought the controller back to the process, but you can see that nothing has changed. So the root cause was not found yet. Eventually, the root cause was a steam trap that was not sealing. This steam trap was the feed to this evaporator, but when it's working well, only the water goes into this evaporator. But since it was not sealing, so the gases were transferring as well, and therefore there was a rise in the temperature and a different behavior. Now you can see here that Samguard provided repeating indication until the problem was resolved. We didn't left this event until it was resolved, and Samguard just repeated and sent more events about it. And together with the AMC follow-up, it ensured that nobody will drop the ball. Next case is talking about a furnace fan speed electrical issue. You are looking at the fan speed, and you can see that on the left part of the screen, it is very stable. But then you can see that there is a drop in the speed for just 1 hour, not a big one. And the controlling room didn't detect any of it. Now you can, okay, I will get to the end. The reason I took it to the process engineer. The process engineer took it to the electrician guy, and eventually the electrician guy referred this problem to a resistor, and it was replaced. Now, this is a very good example for a very, very small event that you cannot find when you have rules, because you could not think about such a thing. But actually, it can prevent a future huge event. Now, I see here the limitation of the traditional controlling system, because it is relying on rules, on limits, process limits that we, the human beings, thought about. But Samguard algorithm is actually scanning without any limitation of predefined alerts and predefined limits. And Samguard algorithm, together with the AMC attention, detected the electrical issue. Next case is talking about a compressor oil pressure increase. You can see on the green line that it is pretty stable, but then we start to see some peaks. Now, this is, first of all, we're talking about a very, very important unit in the process, a critical one, which might result with a flare in case of shutdown. And it is so important that you can see that actually there are 3 points of measurement at this oil pressure. But again, the traditional controlling system is actually built on rules, and the rules were for decrease of the pressure and for a combination of pairs of tags. But Samguard is making an overall plant scanning. It's including the critical units and the small units, and it's really scanning objectively. Doesn't matter if it is a noisy part or a quiet part. And here, there was a faulty sensor. So one of the 3 points were actually faulty sensor. So here we found a major failure potential that could have been overlooked without the AMC. So if we conclude all the events that we saw, you can see that I presented all kinds of events of critical units, of less critical units. I presented the things that are, we found them very small, or things that we found them in the, when already the failure is developing quickly. And if I can summarize all, as I see that really the added value of the AMC is that in each of the cases, Samguard provided a pinpointed alert, but what really made the difference was that the AMC took ownership over the value creation process. Thank you. That's it from my side.
Thank you very much, Maya. I hope this was insightful for all of you listening. And I guess this is kind of bringing from the high level of saying, okay, there is value in predictive maintenance. Yeah, we can identify the problems, all these small problems that otherwise you would miss. And yes, you need somebody to, as Maya mentioned, to take ownership, actually to the real examples and the real value which was created for customers. I would like to kind of conclude in one slide about how it is really implemented, because and I think this is, while Maya was speaking, I was looking at the Q&A and I saw one question about how come it's so fast to actually implement and take all these thousands of sensors into the system. And it is fast. Okay, so just to summarize, how can you get to this to actually a working service? It all starts, of course, you have the data in the historian. You create a Linux server. By the way, we are not, those who are saying cloud only and nothing else. Actually, about 60% of our customers are running on their own network, on their own servers. The other 40% is running in the cloud or on our servers, whatever you want. Any server will do. We just need the server. We basically load the 13 months of data. You don't need to select tags. You don't need to select which ones you think are important, which ones are not, which ones are good, bad. Just put everything, all the relevant data into the server. The process that is happening in parallel is that we model. Now, we are working for many, many years in order to make this simple, okay? And the model that we're creating here is, first of all, it's very simple, it's very intuitive, and it provides us the minimal amount of data that we need, or the software need, in order to give you the most pinpointed alerts, okay? It doesn't allow for simulation. If you look at this model, you wouldn't know which material is being produced here. And probably, and for sure, you wouldn't know what's really the chemical processes that are going on there. What you would know is what the hierarchy of the plant, okay, what are the parts and subparts, and what is measured where, and what are the main processes and the effects between the different things, okay? And this is all we need, and this is why it takes such a very, very short time. And the idea behind building it as a service is that it really requires a minimal amount of effort on your side, because once we have the PNIDs, we can conclude the static part of the plant, and with minimal question answers from the process engineers on site, we can conclude the model in a very fast way. And a 2 weeks exercise is what we did on and on and on in many projects. Before COVID, it was something that we usually did on site, came to the plant. Now in the COVID era, we implemented plants over remotely. Both ways will work, and this is the time it takes. So at this point, we have the historical data for the machine learning to work. We have the model of the plant. Now we connect the live data, and it can be through file transfer or APIs, depends on which historian you're using, and that's it. Okay, and from here on, we're basically ready to go. The service is on, and from here, Either you do it yourself internally, or you use the AMC. And 2 or 3 weeks from now, let's say a month, because it takes you some time to create the server and convince the IT. A month from now, you can be with the service on. But as I said, and then we said throughout this presentation, this is only the beginning. Okay, the real work begins when the technology is already implemented, and now it's actually the main work for a PDM project, because successful PDM project really involves cultural change, and not just a great technology. So with that, I would like to conclude and move to your questions. And here are some of the questions from the audience. So if you would like to ask a question, feel free to write it down in the chat or in the Q&A below, and we'll be happy to answer them. Okay, so I'll give you another second to just answer. Ooh, to just add more. Okay, so let's start with there is a question here about the existing DCS and SIS system. And is there a intention in the future to cover the functions of DCS and SS? I would say to that the following. Today it's a side-by-side. Okay, you have your DCS, you have to have your DCS, and you have control, and you have your alerts on the DCS. One of the things we are considering and we are looking at, it's very clear that the rules, as Maya mentioned before, the rules in the DCS cannot cover everything. And of course, the rules that you can create using the machine learning, which is relearning and relearning and relearning all the time, will be much more accurate and will prevent some of the alert fatigue that you're getting on the DCS. And will give you a much better response. Is this process is something that I think people will implement today? Probably not. Okay, probably it will take some time of working side by side, but eventually I'm sure the DCS alerts will be based on machine learning and AI, and not just on the pre-programmed rules that that were programmed there. So I would say another question. There is a question here of the examples of 2, 3 process variables to detect a problem. Are you using machine learning or a Boolean type rule-based agent to detect with only few process variables? I would, when you make a presentation, you always have the dissonance between trying to explain how complex things are in the background and making it very simple in the foreground. And actually, we have the same thing within the application, because in the background, we're not looking at these 2 tags. We're looking at sometimes tens or hundreds or thousands of tens of thousands of tags all the time. Okay, from all these tens of thousands of tags, we decide, okay, we think here in this part, in this pump, in this valve, in this whatever, there is a problem. Now we're looking within the tags which are related to this equipment, which are the tags that will be most clear, most apparent to the user in order to determine the root cause. Okay, so the fact that you're seeing there 2 tags, and somebody asked about what lesson learned, the fact that you're seeing there 2 tags is work of many algorithms that take from all this noise and try to bring you only the ones which are relevant for your analysis. At the beginning, we were presenting tens of tags and told the user, oh, we're sure that the user would know how to differentiate and how to look at it. It didn't work. Okay, so the software is smart enough in order to bring only the ones which are relevant for your analysis, but it doesn't mean that these are the tags that actually initiate the problem or created the problem, or this is the tags that the system is looking at. There is a question here about any special consideration for batch process versus continuous. Yes, yes and no. We do both continuous and batch processing. I think I even have one plant which has both batch and continuous at the same plant. In general, we see that the batch processing is a little bit more noisy in terms of false alarms than the continuous ones. And when we refer to batch processes, it's also important to know that any machine learning, in order to actually work, would need some kind of historical data. And what it means here is that if you're changing products on your batch processing every 2 weeks, and every time it's a new type of product, you may have a problem implementing predictive maintenance because the historical process data is not sufficient. I'm just browsing through the questions to see.
Question about the causality graph. Explain a bit more about the causality graph and how it's constructed.
Okay, there is a question here about okay, there is a question here. Do you do anomaly detection and or in addition to Boolean basic rules? Okay, we don't do Boolean basic rules at all. There is no one rule in the system that was predefined. Okay, all of it is basically based on the two things: the anomaly detection and the causality graph, which we created at the beginning by describing the plant. Everything is based on these two things. Do we interface with the CMMS and email or text notification? Yes, we do. We interface with whatever you would like us to interface. And of course, the major tools like SAP and so on, and the emails and then text notifications is a non-issue. Yeah, no. There is a question here: can the system work without the cloud? Yes, we can work. It's your decision whether you want the server to be installed on your network, on our network, on the cloud, on Amazon Azure. It's really up to you. There is a question here: what do you think about prescriptive maintenance? How mature is it? And are you implementing it? Okay, so again, it depends on the industry. In the industries that we are working in, and that's the process industry, and you just heard from Maya a few examples where first the machine learning worked and gave an alert, and then a person looked at it and still made the wrong decision. And then when they made the right decision, there were several options of how to address the problem. Should we address it now? Should we address it later? Should we change? Should we do this? Should we do that? So, and all of that are for cases that never happened before. Okay, all the examples, all the equipment that we showed that actually had the problem, never had the problem before. So I would assume that if we're successful with providing an early alert where the person can actually decide what to do, we made a huge progress for the process industry and huge progress for the plant. So instead of reacting to fires all the time, if we gave them an early alert and they made the decision, this is, for sure good enough, at least for the next, let's say, 5 years, for sure. whether it mature for that later on, maybe. I still cannot see the technology that will actually bring to it. With the time a little bit pressing, what is an AI causality graph? Okay, so without going into too many details, I would say the following. When you're talking about data, you usually think about the correlations. Yeah, you think when one parameter is going up and another parameter there is going up, they're probably related because they are correlated. They're moving together. And if you look at the internet about correlations, you'll see that there are very funny examples of different parameters which look correlated, and they are correlated from statistical perspective, but they're completely unconnected. Okay, the bananas somewhere and the diaper somewhere else, and there are tons of examples like that. The purpose of the causality graph is to avoid these kind of correlations. Okay, we know unlike any other place, internet and so on, we actually know what is affecting what. Okay, you know that when you increase the set point here, the temperature or the level will go up there. So why not use that in order to really narrow down the possibilities that the machine learning will look at? Okay, which is actually what we are as humans are doing when we look at data. So the causality graph is basically ignoring or not taking into consideration the correlations. It actually takes the knowledge that you already have. You know that this is affecting that, and this is what we articulate in a very fast process to the minimal level that we need within the graph. Do we have time for another? Okay, there is, in this presentation, we try to show, or we demonstrated how well predictive maintenance can be implemented through an analytical monitoring center. Yet, I must emphasize that we have many customers that are not using analytical monitoring center, and the team in the plant is using the software, looking at the screens, deciding what to do, paying attention, taking ownership over the alerts, closing them, evaluating them. Everything is running very smoothly. The two things that, and as I mentioned, you need to remember is one, management support. Okay, it requires management support, and the second thing is time. If you're asking a process engineer on site to actually look at the new tool, you need to allow this person time to do that, and this means that some other tasks will need to be removed. So I would say we have about 50-50 in terms of projects that are internal versus projects which are through the AMC, and they both work, but you need to really evaluate your organization, your plans, in order to decide which option is better for you.
Great. Perfect. Thank you so much, Shen. And that is all we have time for today. Thank you to everyone that has joined. We hope that you found the webinar insightful. If you want to rewatch the webinar, you will be sent the recording and slides next week. And thank you also to our speakers, Shen and Maya. If we didn't get time to answer your questions, the team will get in touch with you to answer this. Have a good evening, and keep an eye out for future Reuters events content that you can also sign up to. Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye.